So this is a problem from the 2008 BC exam. It was on Form B that year, and it was a calculator question. And it's a parametrically based problem. They give us a setup that's pretty typical of a lot of these free response questions that you can find on the College Board's website. But we've got a particle moving along a curve in the xy plane. The curve is defined parametrically by x of t and y of t. So the x component of position is given by some function of t. The y component of position is given by some function of t. And those functions hold for t's that are positive. They give us the rate of change of the x component of position, dx dt, and also the rate of change of the y component of position, dy dt. So really what they provide us with here is they provide us with the velocity in the x direction and the velocity in the y direction to answer all the questions that they've set up for us. The only extra little tidbit of information that they give us is that the particle has this as its position at t equals 4, so an x coordinate of 1 and a y coordinate of 5 at t equals 4. Part A asks us to find the acceleration vector at a certain moment in time at t is equal to 4. And so the position is determined by x of t, y of t. The velocity vector would be determined by dx dt, dy dt. Therefore, the acceleration vector is going to also have an x component determined by the second derivative of x with respect to t, and a y component determined by the second derivative of y with respect to t. You can definitely try to carry the derivatives out by hand, right? Derivative of this would need a chain rule. Derivative of this would also need a chain rule. If the calculator's in play, though, you can definitely use the calculator's capability of numerically evaluating a derivative at a certain point for you. And we can definitely do that here. You see my screenshot from my calculator, my TI-83. I found the derivative of this, derivative of dx dt, evaluated at 4 to determine my x component of acceleration, and then the derivative of this evaluated at 4 to determine my y component of acceleration. As we move ahead to part B, it asks us to find the y-coordinate of the position of the particle at time 0. So this is kind of weird because we want the initial y-coordinate of the object, assuming that time began at 0 here. And what we have access to is we have the position of the particle at time t is equal to 4. So this is kind of weird because we're going from a t-value of 4 back in time to a t-value of 0. Most of the time when you do problems involving velocity or just rates of change in general over time, you're always working forward in time. And so a calculation that you can probably buy into is you could determine the y component of position at 4, y of 4, by taking the initial y coordinate, y of 0, and adding how much the y coordinate changed from 0 to 4 by integrating the rate of change of the y coordinate of the object, by integrating the velocity in the y direction. If I want to figure out what this is right here, if this equation holds, which it does, I should be able to subtract this integral from y of 4 in order to solve for y of 0. And that's exactly what I did on this next line. Y of 4 is 5, so I took the 5 from y of 4 minus that definite integral. I definitely did that computation on the calculator once again, and I got an answer of 1.601. For the initial y coordinate of the object. Alternatively, what you can do here is you can say y of 0 is equal to y of 4 plus how much the object's y coordinate changed from 4 working back in time to 0. And if you're thinking about it, the reason why this computation is going to give us the exact same result as the one that I actually carried out on the previous line is because if I have these limits of integration and I would like to exchange them with each other, put the 4 to the top, the 0 to the bottom, then I would have to change the sign out in front of the integral from addition to subtraction. So whatever way is easiest for you to think of it, both of them are going to give you the same result. They both simplify to each other, but you get 1.601 for the y coordinate of the object at 0. In part C, they tell us that we are considering the interval from 0 to 4 for t, and we want to determine the time when the speed of the particle first reaches 3.5. So if you know how to go from velocity to speed, velocity components to speed, it's just basically by resolving a vector and finding its magnitude. If I use my speed formula by resolving my vector and using the magnitude of the velocity vector for speed, I get this expression for speed. And if I apply this expression to these specific components, dx dt and dy dt, it ends up simplifying to this right here. And so what I went ahead and did is, since the calculator was in play, I wanted to set my speed equal to 3.5. And so I went ahead and I graphed the constant line value 3.5, and then I graphed my speed function. And the first time that the speed was equal to 3.5, I used intersect on the calculator to determine it, and I got 2.226 for that result. And obviously you see that speed was equal to 3.5 several more times. Now we might be extending out beyond 4 eventually here, but we just wanted the first time that the speed reached 3.5, and that's 2.226. And then the last question here asks about the total distance traveled by the particle on the interval from 0 to 4. Well, if you've ever done the one-dimensional versions of these problems, which I'm sure you have, you would integrate speed, or the absolute value of velocity, across the appropriate limits of integration, in this case 0 and 4, to determine the total distance that the object traveled. In this case, we're going to do the same thing. We're going to integrate speed across the interval from 0 to 4, and that's going to amount to us throwing the expression that you saw on the previous screen for speed in as our integrand. We do that integral from 0 to 4. I did carry that out on the calculator. I did it from the graph screen. I already had this graphed from part C, so rather than going back to the home screen and using numerical derivative option, I went ahead and I used the function integrator option. I used the integral option from out of the calculate menu after I took the line y equals 3.5 off my graph, and I ended up getting 13.182 for that total distance traveled.